Hello, guys. Don't mind me, I'm just eating some potato skins. Okay, we're going to discuss transformers. This won't take long. In fact, I'm not even going to set a timer. This will finish up our catch up lectures, and then we'll start in on chapter 24 tomorrow. And I think that'll do it. So, transformers, section 23.7. So, the symbol for a transformer in a circuit, and this has nothing to do with the circuit, but this is a transformer. Okay, so current is going to come in on one side. Okay, we could call this current 1. And it's going to go down and essentially go back out. What a transformer will do is it'll cause another current. It will induce another current through the use of inductors or solenoids, however you want to call it, solenoids. And this other current, I2, will be what comes out of the transformer. So the current going in and the current coming out are going to be different. But what that means is also the voltage going in, so we could call this V1, from this point to this point, is different than V2 from that point to that point. So transformer will change our voltages. Of course, the current has to change as well, but okay, no, don't eat the potato skin. You got it's very tempting. All right, so the reason that the page is so low at this point is because I'm hiding my drawing. At first I thought, oh, that's a great drawing for an 8-year-old. Anyway, here it is in all of its glory. Well, not quite all of it yet. I do want to point out this right here. This little bit right in here, these two lines, that represents the magnet, or I'm sorry, the steel or iron or metal or whatever you want to put in between the two coils. I don't know if you guys remember, but we had the solenoids at school and we took the inner solenoid out and we had the outer solenoid. Well, that's basically a transformer. So you go in with one set of coils and then you come out with the other set of coils, and the transformer gets better because you have, on the inside, you put the metal steel rod down the middle. That makes your transformer better. So that's what those two lines are in between. It just represents the metal that you're dealing with, as far as I know. But I might be wrong. If other people know more about it than me, that's fine. But I think that's what those things represent. Because you sometimes see a transformer without those. And I think it's just that it doesn't have the metal rod between it. Okay, whatever. Here nor there, let's talk about generating. So last couple of, we've been talking about generators lately. So we understand how generators work. So let's say we have some energy, we've got potential energy that we want to capture, like in a dam. So we let the water in one side and we let it flow out the other side, and it's rushing through. It's got some velocity as it's going through. And right in here, we have some turbines. So those turbines will spin around, doing the thing that we've been talking about, generating our electricity. And that electricity gets generated and will come out in a current, okay? And it's generated roughly around this 10,000 volts, okay? Let's just say 10,000 volts. You can look up what generators do and then imagine a whole battery of generators all producing what they normally would produce, so you get 10,000 volts. So you do that, you have this current that's coming out, it is going in here, we can call it I1. We're going to oscillate back and forth between I1 and I2. So we're going to go to I2 now, and we're stepping up to 10 million volts, 10 megavolts, okay? When we do that, we already talked about why, so that we can go long distance, right? So we go, we want our I, here, let's call it I long distance. Okay, so we've got ILD, and it's going to go all the way down. We've got our ILD. It's coming in hot. It's actually, if I do this right, it's going to be going back this way and coming in this way. All right. High voltage means not a lot of current. Okay, so the current kind of goes down, but the voltage is really high, and that's all that matters. Then we get to this point here. Within about 5 to 10 miles of your house, you see these stations all around, transformer stations. You'll notice there's these things, and you'll be like, why is all this? What is all this? Well, it's a transformer station, and it's stepping down the really high voltages down to, I don't know, 10,000 volts near your house. And that way, most of the power isn't lost as it comes from the dam to the local neighborhood. So it comes from the local neighborhood. We've got more current happening. So here goes our current taking off down there. And our current comes in here to another step-down transformer. That step-down transformer takes us from 10,000 volts to 440 volts in your neighborhood. So the current comes in, goes out there, and we have another current that will come to a final step down. I shouldn't say final. It's a step down that is near your house, like on your street or somewhere pretty close to your house. So that happens, and the current comes in and goes out, and that current comes in and goes out toward your house. And in your house, then you have this 220 volts, and literally this happens on your street, okay? So that step down thing happens just like really close, and goes into your lovely house. You wish your house looked that good. I'm just kidding you. I'm sure it's wonderful. Probably even better than that. My drawings aren't great. Here, if I was drawing, I would put the sun. All right. I really do feel like I'm in 8th grade. No, 2nd grade. Okay. Your house has 220 volts that comes in. It can get cut in half. They have, you might call it another transformer, where they give, the box in your house has 220 volts on it, and they split it up. So they have one side gets 220 volts to the other side, but then they have this halfway in between. It's kind of like having a transformer in that box, and you can cut it so that you only get half the voltage. So most of your outlets at your house have that 110 volts because they've cut it in half. You can, you'll have some things in your house that use the full 220 like your dryer on your clothes dryer. Okay, so that's basically what happens. If you want to plug in your hair dryer or anything, then you've got that 110 volts, which your hair dryer is completely designed to do. If you were to go to Europe, so you're all lucky, you're psyched, you're going to go to Rome. No, Barcelona. So you go to Barcelona and you want to plug in your hair dryer because you got to look good for everybody there. And I would spell Barcelona, but I don't know how. And they pronounce it Barcelona, believe it or not. Okay. So then you get this plug, right? That's weird because it's weird European plugs type stuff. I don't even know how I would draw it. But anyway, so you have some plug you can plug in. And this thing is also a transformer, okay? Because they use 240 volts at their houses, right? We decided we wanted to do this. Why would we want to do that? Because we're idiots and we're smart enough to know that, and we're smart enough to make sure that the voltages are small when we go sticking our hair clips in the outlets. So we want small voltages so that, nobody really dies from this. Although every once in a while someone does, but not very often. So we've got these other boxes, and you can plug your own plug in to that box, and then you can run this to your hair dryer. Oh gosh, am I going to try and draw a hair dryer? Oh my goodness, I was able to do it. Okay, so there's your hair dryer, and fine. So you plug this into this transformer that steps it down from 220 volts or 240 volts. It steps it down to what we really need for your hair dryer is 110 volts. I don't know if you guys have seen it, but there are switches on your hair dryers or other assorted items in your house that you plug in, and you can see there's a switch, and it'll say 240 or 120 or 110, 115, something like that. And you can switch back and forth, and then you don't really need the transformer to go to Europe, okay? Because you can just switch it to the 240 volt, and then your hairdryer works fine because inside your hairdryer you have a transformer. So that is everything I know about transformers. Oh no, not quite. Okay, so how does a transformer work? I should have spent less time drawing that picture and more time drawing this picture that I'm about to do. So here we go. An old style transformer doesn't look like the solenoid transformer that you guys took apart for your experiment the other day. It looks like this. And if you've ever taken apart a receiver on like on some electrical equipment, you've noticed that inside there's this thing that's a brick of, it's heavy. It's made out of iron, and it's done in sheets, which is pretty cool. So there's these sheets, that separate these plates, and they're all kind of glued together, but in between the sheets is a, we got a couple more in there. All the sheets have to match. In between is an insulated material that doesn't allow the current to flow from one sheet to the next. All right? But this isn't where the magic happens. All that does is keep the eddy currents, you guys know about eddy currents, keeps the eddy currents down, okay? So here's where the real stuff happens. So we have, on one side, we have some current coming in our wire, and our wire is going to go around this thing, and it's going to do loops. And it does a lot of loops. You guys saw those solenoids. One of them has, 3,000 loops or something on it. And the other one has like 150 or something. And then this goes back. So our current would flow in and then out. And we can call this current I1. And we would call the voltage difference between there and there V1. And then on the other side, you have a similar thing. So, but this time, let's see, do we want step up or step down? It doesn't matter. We can go one way and then go the other way. Okay. All right, and I need to connect this to something. Okay, so on this side, we have N1 loops. Over on this side, we have N2 loops. And here we have a current I2. And here we have the difference, the voltage difference from there to there. That is V2. Okay. So far, so good. Now, there's all kinds, I'm calling it N1 and N2, and I'm calling it that for a reason. Because depending on our situation, all right, well, let's first talk a little bit about this ferromagnetic material. So pretty much ferromagnetic meaning iron. So it's iron or steel, something like that. That's fine. And our current will flow in some way through the iron or steel. And that current, those loops, those eddy currents that come about due to Faraday's law of induction, drives current in the other side. And that current then leads to our voltage on the other side and our current on the other side. So we want the eddies to go in like this. Okay, we want the eddy current to go like that. We don't want it to ball up. Okay, so having balled up eddies is bad because that's just a loss of energy, right? So you want the eddy to go all the way around, and you also don't want the eddy to get squirrely and go sideways like this. So like this through. That's why you cut it into sheets, and you don't allow current to flow. You've got insulators in between the sheets that doesn't allow current to flow. So you get a very good current flow through your transformer. Okay, so Faraday's law of induction. That says we've got, let's just deal with our V2 for a second. So V2 is equal to, and we'll call this side N2, this side N1. So V2 is equal to minus N2 times delta phi over delta T. All right, so that's the first one. But we're going to do the same thing on the other side for V1, and that's equal to minus N1 delta phi over delta T. The key here is to realize that this current loop that's going around is the same for both sides. So I2 and V2 and I1 and V1 both get this inducted current change in flux, okay? So this change in flux is equal to this change in flux. So now we can do something pretty neat, and we can say that V2 over V1 is equal to N2 over N1. So all it matters is the number of loops that we have wrapped around this thing. That's why I put a different number. What do we have here? 1, 2, 3, 4, 5. So we have 5 loops going around the right side, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 going on the other side. So 5 over 9. Okay, so now we can say, oh, V2 equals 5/9 of V1. So if V1 has, let's make it easy, 100, does that make it easy? What's 9? Here, let's do 45. 9 times 5 is 45. Is that going to help? Is that going to make it easy? I don't know. So let's say V1 is 45. Does that make it easy? We get 5 times 5 is 25. Yeah, okay. So V1 equals 45 volts. So what does that make V2? V2 is equal to 5 times 5 is 25 volts. So we came in with V1 bigger than V2. All right, so what does that mean? That means if V1 is bigger than V2, and we're going from V1 to V2, then we have just made a step down transformer. Now, let's say that we switch them. We're going to switch it, and we're going to now call V2. Let's just get rid of all this. Don't make me regret it. Okay. So let's say that V2 is now our V in. Okay, so we're starting with V2, all right? And that's our V in. V1 is equal to our V out. So what did we have? We wrote down that V2 over V1 equals 5/9. And but now we've got V1 is the final out. So we're starting with V in equals 25 volts. And our V out is 45 volts. And so that means that we have come in this way and we're going out this way. And what we've done is we've stepped down our voltage. So a transformer is nice because you can run them in reverse. You can go forward, backward, and you get a lot of good work out of a transformer. They're cheap. They're easy to build. There's a lot of good reasons why you want to use transformers to do all the things that we want to do. So I'm going to draw a line on the page. All right. So what we can say then is V out over V in is equal to N out over N in. Okay? And no matter what happens, that will work for you. So you don't have to name one side V1, one side V2. You just know which way it's going in. Whether it's a step up or step down will be determined by the number of loops that you have. This equation right here, this is called the transformer equation. The transformer equation. Okay, so that's very helpful and pretty easy, right? That's an easy transformer equation. It's very nice. So let's just make N out greater than N in. And so then that way V out is greater than V in. So if V out is greater than V in, we have stepped up. Okay? And we can do the same thing. We can turn it around and say that N out is less than N in. V out then is less than V in. And we have a step down. All right. So, let's look at the power, but we want to note that while we're looking at this power, the resistance inside the transformer is very small, okay? We want that resistance of a transformer. We want it to be very easy for the electrons to do their thing. We don't want them to be hindered. So we want it to be very, very small. So we're discounting it, in other words. We're not even thinking about the resistance of the transformer itself. So let's talk about the power situation. So we have P in, that's equal to our current going in and our voltage going in. And if we say that that is equal to our V out, our P out, I'm sorry, okay, so this, the power going in has to be equal to the power going out because there's no power lost in the transformer itself. So that means that this has to equal this. That's very convenient for us. And we can generate some more equations and figure out what current has done, okay? So now we can say that V out over V in is equal to I in over I out. Okay, so it's an inverse proportionality, all right? And that also means that since N in and N out have the same ratio as V and in and out, we can say that, all right? So these equations work well, all right? And you can compare the current. A lot of the times you'll be asked for the current and the number of wraps around on one side, the loops on one side, or the current or the voltages on one side. So it all depends on what you're given. And this is the relationship. Just think about it as the current is the upside down one. Okay? The other two go in line with each other. The current is upside down. Okay, well, it's time for an example. Let's go. Yeah, let's leave it like that. Okay, so let's do our example. Example 23.5 out of the book. We have an X-ray unit. Has, so X-ray unit has V in equal to 120 volts. It needs V out equal to 100,000 volts. All right? So it can produce X-rays. That seems about right. We're given that N in, not 9-inch nails, it's N in equals 50 loops. And I in is equal to 10 amps. So a lot of amps, pushing a lot of amps on this one. Okay. So first question, and you guys should pause and get these right. I mean, seriously, have you guys dealt with anything easier than this, these ratios? Pretty slick, right? First question, what is, you can probably even do it in your head before I even get it all written down. What is N out? And B, we want what is I out? Okay. N out. So we know in and out for the voltages. So we're going to put, let's just put V in over V out is equal to N in over N out. And we want N out, so we can rearrange that. And we could say that N out is equal to N in times V out over V in. Did I do that right? I think so. Okay. So all we have to do is plug in the numbers. N out. This is for A, by the way. So N out, what is that? Equal to N in. We know what N in is, 50 loops. So we're going to take 50. We've got V out. So that's 100 times 10 to the 3 volts. And in, we've got 120 volts. So our volts can cancel. And we're left with the number of loops. 100 is 10 to the 2. So that's 10 to the 5 divided by 120. It seems like a lot, and it is. It's about 4.17 times 10 to the 4 loops. All right, so that's our N out. So let's say equals N out. We can box that in there. Okay. So B, what is I out? Well, we kind of want to write down the equation, right? So, well, let's not reinvent the wheel. We want to solve this equation for I out. We put I out up on the top. We've got I in on the other side. V in times it divided by V out. So give me this. I out equals I in times V in divided by V out. You know, if you're in doubt about this relationship, just remember that we got it from the fact that P in is equal to P out. And by P, I mean power. Power equals I times V. So P in means I times V in. So those have to kind of go together every single time. And if that's the case, then of course you would just be dividing by V out to get your I out. Okay? So that's a good way to think about it. Now let's just write down what we know. We've got our V in and V out. So we've got I out is equal to 10. Of course, it's amps, right? It's the whole, because the V's cancel. So we're left with just amps. So I'm going to leave 10. And then we've got V in on top, 120 over our 10 to the 5. And then we'll call it amps. And that ends up being I out equals our 12.0 milliamps. Okay. Fine. That's great. We could also do it with the ends. And you're going to end up with a similar situation. You're going to say that I out is equal to I in times N in divided by N out. And hopefully we're going to end up with the same answer, okay? So we're going to say I out. Our I in, again, was 10 amps. And we're multiplying that 10 by 50. And we're dividing by 4.17 times 10 to the 4. And believe it or not, you're going to get 12 milliamps. So not too bad. It all kind of comes out in the wash. Okay. So we've done that. Nice little clean example. Let's do a nice, no, I was going to, nope, forget it. Let's do another nice and clean example. Example 23.6. Okay, this is a step-down transformer. And we've got a battery, and the battery has an EMF. So I'm going to say EMF of the battery is equal to 12.5 voltage DC. And it needs 15 volts in it to charge up the batteries. We start with V in at 120 volts. How many loops are needed if N in is 200 for an N out? Okay, so we want an N out. So we've got 12.5 volts DC and needs 15 volts in to charge up batteries. So what are we going to do? We're going to make a transformer that gives us this. We're looking for 15.0 volts is going in. And we want to charge up a battery. So this is our battery we want to charge. And we start, what? Oh, I'm sorry. That is not V in, that's V out. Jeez. Because that has to be the thing that we charge up this battery with. Okay, so what a... let's start over. We've got V in is equal to 120 volts. All right, we're going to run that through a transformer. And we're going to come out with 15 volts. Which is what we need to charge up our battery. Nice. So, N in is equal to 200 loops. All right. So how many loops are needed for N out? So the question is, what is N out? These things are so easy. You'll never have relationships that are so easy. V out over V in times N in. Cake and pie, baby. N out equals 25 loops. And you should plug that into your calculator to make sure I'm wrong or right, but I'm pretty sure I'm right. 15 times 2 is 30 divided by 12, 2.5. Is that right? Divided by 12. Yep, that's right. 25 loops. Okay. Great. So that's A. B. If we want or need to have 16 amps out, so we need 16.0 amps equals our current out. So a lot of current to charge up the batteries. Okay. If that's the case, what is I in? So we can come back to our old trusty equation, V out over V in is equal to, so V in would be times I in, so we'd say I in over I out. And now we're just going to solve for I in, so that makes it easy. That means V out over V in times I out. And again, if you notice, that's our power on top there. And we just plug all those things in, plug and chug. And in the end, you end up with 2.0 amps. So should we do it? If we plug these in, V out 15, V in 120, and we're going to multiply that by our current, which is 16 amps. And yeah, 2.0. Gosh, I don't know, those numbers don't seem right. Let's see. 15 enter. 16 times 120 divide 2. That's it. 2.0 amps. Okay. So let's see. Do we have anything else? We are going to start chapter 24 tomorrow morning, and then we're going to do our lab. So we are on track. Have a great night, guys.